Hello everyone, I'm Stefano Zacchiroli, co-founder of Software Heritage, but I'm here today with my other hat. I'm a professor of computer science at the Polytechnic Institute of Paris, and I'm going to present to you some work that's been jointly done with colleagues from the INRAD Diverse team in Rennes, Romain Lefebvre, Charlie Roy, which I've seen in the room, and also Olivier Barret and Benoît Combemal. So the previous panel has actually done a lot already to actually save me from going through a long introduction, so thanks a lot for that. Let's start from the observation that open source and free software offers some key freedoms that are very useful in practice for users, in particular those of being able to be freely used, copied, and modified, but they're also super useful in the context of innovation. So open source software is a huge innovation booster, and for instance, it allows you to reduce the time to market for any product that contains software that you want to put on the market. And we see this in practice. So even if we would like all software in the market to be free and open source software, in the software that is not open source software today, we see that 96% of the products actually are based on open source software. So it is really everywhere. And with this increase of exposure in open source software, we also see an increase in scrutiny, both from good actors and from bad actors. With bad actors here, I mean attackers. So open source software is more and more targeted by cyber attackers in a number of ways. It is also being, for that reason, more and more under the eye of regulators, as you have learned from the previous panel. So the executive order by Biden has already been mentioned, the CRA has already been mentioned, and just as an additional fun fact, I learned just a few days ago that one of the very last executive order of Biden, a few days before stepping down, was again on the importance of securing open source software. So the main way in which today open source software is attacked is as part of supply chain attacks. They have already been mentioned here briefly, but let me just give you some additional details about how they usually work. So the main way, one of the main ways in which open source software is used is via dependencies. So you are creating your own product, let's say A in the picture here, it could be open source or not, but for creating that product, you depend on other open source products like B or C here in the picture. And that goes on, creating a long chain or a big tree of dependencies. So that creates a very interesting strategy for attackers that usually do the following thing. They target what are leaf packages in dependency trees, so the package that you don't actually use yourself directly, but they are indirect dependency of your dependency, so kind of far away from your line of sight. And usually they target those packages that are under-maintained, so maybe they don't have a company behind them, they're maintained by some random volunteers, and they try to infiltrate malicious code in those leaf dependency packages. Once the malicious code is there, they wait for the real target to actually install the malicious leaf package, and at that point, they have some nefarious code that entered into some high-profile targets they have. This technique has been used very often in the last few years. It's increasing in frequency, and it leads to several attacks, which I'm not going to describe here, like EventStream, NodeIPC, or XZUtils just last year, which actually resulted in multi-billions of dollars of damage. So this is huge. So what can we do about that? And specifically, what can Software Heritage do to help with that? So Software Heritage already by design offers some key properties that are super useful for securing software. It provides availability of open source software that you might depend on, and that alone is already very useful if you need to be able to always retrieve a piece of open source software to be able to deploy something. The fact that there is someone guaranteeing that it remains available is already very useful to guarantee that you don't have downtimes. It guarantees integrity. So the software hash identifiers have already been mentioned multiple times. It guarantees that when you retrieve something, you can check that it has not been tampered with respect to the last time you checked. And it also guarantees traceability, so you know where code comes from, and that's another key ingredient when creating documents such as the software bill of material. But it's actually more than that, and Mike, I think, already alluded that in the panel, and it provides a universal open knowledge base about facts for open source software that can have very important applications in cybersecurity. And it's important to say here that it's also data that we made available openly as Software Heritage, so that enhancing security is not something that only big companies or big players can do, but actually everyone, including researchers, can do and help others in securing their software. So this is the main vision of the Software Heritage Security Project. It's been financed by the French National Campus Cyber. It started at the end of 2023. It funds 8 research teams, including the Software Heritage Core team, and it has multiple axes, which I'm not going to detail here, don't worry about that. So the first axe is increasing the amount of information available in software heritage to add information that is relevant for cybersecurity. And then there are more proper research axes, one of which is vulnerability tracking, which is the one that I'm going to focus on for the rest of my presentation. So usually, many people worry about so-called zero-day vulnerabilities, which are vulnerabilities that are in your software and you don't know that are there. But actually, a lot of damage can be done via one-day vulnerabilities. So one-day vulnerabilities are vulnerabilities that are publicly known. We know they exist. We know in which piece of software they are. We usually know also how to fix them, but they are still present in software you care about. Maybe not directly in the software you use, but maybe in one of their dependencies. So the challenge with one-day vulnerability is identifying them very quickly, thoroughly, and then once you know they affect software you care about, apply countermeasures. There are several tools today available to detect one-day vulnerabilities, but they usually work on declared dependencies. So you look at your piece of code, you know what dependencies are declared in the metadata for that piece of software, and if one of them, or recursively one of their transitive dependencies, is known to be vulnerable by something, you raise a flag. If you use platforms like GitLab or GitHub these days, they usually can flag these kind of vulnerabilities for you. The problem is that there are also other ways of reusing open source software, and one popular way is what is called forking. So one can create a piece of software. For instance, here I'm taking the real example of a DDNet video game, which is an open source game available from some major gaming platform on the market, which is based on another open source game called T-Words. And the idea is that you start from a specific version of a piece of code, you copy all the code and all its development history, and you create new versions. So here in the diagram, when you go from left to right, every circle is a new version of a software. The blue part are all the available versions of T-Word, and the white parts are the versions of DDNet. So it started on the left, copying the code from a version of T-Word, and then periodically to release new version, potentially integrating changes from the original game. And this is all possible and allowed thanks to the freedoms offered by free and open source software. But what happens if when you start from an existing project, it contained a vulnerability? Well, the vulnerability you started from is still there in your code, and it propagates to the new application. So for instance, here, if we imagine that the red versions in the diagram were vulnerable at the moment the DDNet code was forked from T-Word, well, the vulnerability also impacts the forked code. And it will continue to impact it until you merge, so you integrate the changes from another version of the original game that contains the fix for the vulnerability. So we can leverage all that in the context of software heritage. We can start from a public database of vulnerabilities that are known to be introduced into specific commits and fixed into specific software versions and fixed in other software versions, and essentially color the entire graph of code development history, which is already archived today by software heritage, to detect which forks of specific pieces of code existing today are still vulnerable to vulnerabilities that have been fixed elsewhere. Once we have detected that, we can go and inform the maintainers of those forks, and probably in most cases they will be interested in fixing them. It's important to know that software heritage is the only place today where this can be done in a way that is independent from a specific development platform and also cross forks. So we can detect some vulnerabilities. Session expired. Is it me? So I'm just quickly wrapping up. So it's important to know that we can do that in software heritage also in a way like this. So for instance, we can detect some code that was originally developed on a GitHub repository and then forked to a specific GitLab instance, or vice versa, and also across all the 5,000 or more development platforms that we archive today. So some early result of this. So we started from the OSV Dev public database of vulnerabilities, which is provided by Google. We use it to color the software heritage graph. We identified more than 2 million forked projects containing at least one vulnerable commit. And among those, about more than 1 million forks were still vulnerable in their most recent version, which means that the vulnerability that they inherited from the original project were still present in the most recent version of the forked project. Among them, we focused on the most popular ones. So we manually vetted more than 60 vulnerabilities, and among them, 5 were confirmed actual vulnerabilities. We informed the maintainers, and in most cases, they've been fixed. So this is it. The vision here is that we can leverage all the information we have in software heritage to make the world of software more secure, and we can do that in a way that is superior in terms of coverage and applicability than what standard state-of-the-art tools can do. So thanks a lot for your attention.